Okay, so we can make this start. So let me continue with this random matrix theory we've been doing. See? So we introduced this space Hn is by n Hermitian matrices. All right. Then we introduce a probability measure on this space. D mu of H was like 1 over Z. Exponential of minus 1/2 trace of H squared d v of H. This is the Lebesgue measure on this lattice space. Dimension and squared. This is the weight, the kind of Gaussian weight. And Z is the normalization, which is gives the total mass of probability measure equal to 1. And Z is the partition function or normalizing factor for now. It's just this one. It's 1/2 trace of H squared dv of H over H in right? Actually, we calculated that integral using formulas for Gaussian integrals from first lecture.
Does HN have a R measure as well?
What's that?
Does HN have a R measure?
HN?
Yeah.
By R measure, you mean like with respect to what group structure?
Multiplication.
It's not.
I don't know if it's closed.
No, it's not closed. No. It's only a vector space, but there is an Euclidean inner product that I will come to that later. But it's really like a flat space. So I talked about it. This is isomorphic to Rn squared actually, and that's the Lebesgue measure that's taken from the other parts. Yeah. Right. Okay, so that's that. This is called the GUE for Gaussian unitary ensemble, which is this one. Okay, so we also computed some correlations, fundamental ones, proved last lecture that the expectation value of Hij, HKL, which is by definition nothing but integral over Hn, is functions on matrices Hij, HKL, d mu of H. This is just expectation value of this function over this, so we can see this as random variables, and these are joint probability distribution. Yeah, moment of these two random variables. We calculated this. We saw that this is actually equal to 1 only if this matches this one. Only if j equal to k and I equal to L. Right? And is 0 otherwise. Right? We saw that using we wrote this in terms of xij, yij, the components. Okay, so now today our goal is to compute some more expectation values. So compute tracial moments. These are expectation values, rates of HM, basically for all M. Rates of HM for all M, equal to 1. Right? And then we will relate this to topology of surfaces. And relate it to the surface topology. Surfaces, in the usual Feynman integrals for Gaussian things, so we relate it to graphs. These two-dimensional ones or double index objects, matrices, they will be related to surfaces. And this is what was discovered by 't Hooft. Okay. So just to warm up, let's calculate one example at least. What is trace of H2? Okay, so what's trace of H2? Well, this is easy because this, we can just write it as sum Hij Hji by definition of trace. It's exactly this one. And Ij from 1 to n. Expectation values is linear, so this comes out. This is sum over all Ij from 1 to n, right? Expectation values of Hij, Hji, right? And by this result that I wrote here, each of these terms is just 1, right? Each of those terms are 1. So when we add them, we are going to get n squared. So this result is n squared. Okay. This is n squared. Okay. So one more case I want to do. This is, let's look at trace of H4, for example. Right? Let's compute trace of H4. Well, by definition, this is what? This is trace of H4. We can write it as products of sums of products of 4 terms now, because H4 to compute the diagonal on H4, you have to do this. So this is sum I, J, K, L from 1 to n, right? And then we have got H, I, J, H, J, K, H, K, L, H, L, I. You see, it circles back in order to compute the trace. You go around the circle. It's a trace. Okay? So this is equal to sum I, J, K, L. I don't write the limits anymore. So this is H and J. Okay, so now, okay, I don't want to write it unnecessarily now. So then we use Wick's theorem. So this is like product of 4 terms, and that's a Gaussian integral. So this can be decomposed as in the following way. So this step is a result of Wick's theorem. This is by Wick's theorem. We can just write it as sums of the following things: Hij, Hjk, and then HKL, HLI, plus. So we just took the first two. Now I take the first and third, HLI by J, HKL, right? And then HJK, HLI. Right? Okay. So it's and then so we're not done. There is one more term, which is I take the first and last and the two middle together this time. So I just get HIJ, HLI times HJK, HKK. And that's okay. So let's look at the first one. The first one is sigma IJKL. So there are like n to the power 4 terms here. Each of these variables, IJK indices, they take n values, so there are n to the 4 possibilities. So let's write it. HIJ, HJK, HKL, HLI. Okay, so let's see when this guy is not zero, because each of these terms are either 0 or 1, right? So let's see when this guy is non-zero. And that's the only possibility to get some non-zero contribution, right? So this is non-zero, so this gives us a non-zero value if I is equal to k. And here these two match, again, k is equal to I. Okay. So there's only one condition, I equal to k. So there are three free parameters now, free indices. So this term is equal to nq. Because each of these terms, when it is non-zero, is 1, and there are n cubed possibilities that they are non-zero. And then that gives us n cubed. Okay, so for this one, we get n cubed. Now let's look at the second one. Sigma I J K L H I J H K L. And then I've got HJK, and then HLI. Okay. So let's see when this guy is non-zero this time. So for this to be non-zero, we must have J equal to K and I equal to N. So J must be equal to K and I must be equal to L. This is for this one, but this also has to be non-zero. So K is equal to I and K is equal to L, I'm sorry. Yeah, and J is equal to I. So we have these four conditions. What these things tell us? They tell me that I is equal to, okay, J is equal to I, first of all. So basically, this tells me that what? There are only one free parameter, which is what? I mean, so this is, so let's write this. So this gives me I equal to J equal to K equal to L. So one free parameter, which is the common value of these things. So they can change now from 1 to n. So this gives me n. Right? This is n. And now let's look at the last one. This sum IJKL. The last step is HIJ, HLI, and then I've got HJK, HLI. KN. But this one, this time, this is non-zero if J is equal to L. There's only one condition, J equal to L. So the other five parameters, they can all be free. So they're N cubed again. So basically, this is also equal to N cubed. Okay. So adding all these things together, we get 2n cubed plus n. So we get the expectation value of trace of H4 is equal to 2n cubed plus n. So now we want to see what's going on with trace of Hm in general. Now, if you look at these arguments that we made here, it's more or less, it should be clear that trace of Hm is a polynomial in N. Is a polynomial in N. But what polynomial? Finding that polynomial exactly is very difficult. We will eventually do that. But for now, the first goal is to identify the leading term of the polynomial. So that's what we want to do. So immediate goal is find the leading term. Polynomial. These are called planar contributions. These are planar terms. So we'll see what this means and why this is called planar very soon. Okay, now the trick is to use again like some graphical language or device. And the graphical device in this case is Polygon gluings. So there is a graphical device. Well, this graphical doesn't mean graph, mathematical sense. Graphical is a colloquial term, just means pictorial device, I should say. It's not really graphs, it's surfaces actually. Graphical device. So it's polygon gluings. Okay. So here just start with an example. Let's take a four-gun square, and the question is, we want to identify pairs of edges to each other and then glue them. So we put some orientation around here, and we want to glue these things. So let me not maybe mention this. It's okay. So there are three ways basically to glue this square into a surface. So this will give us a torus. But it's actually more than a torus because this boundary, when it gets identified on the torus, gives us a graph embedded on the surface. So, and this graph that's embedded on the surface is this one. Okay, so we get an embedded graph on the surface. This is one case. Now, but we can identify these edges in two other ways. Is here. Okay, next we can do the following. We can identify these two. If you identify these two, again, let's see what happens. Notice here we get one vertex, okay? How many edges this graph has? Obviously, 4 divided by 2, because you identify these edges no matter what. And 4 divided by 2 edges. And how many faces? So let's get the graph gamma on the surface. So one vertex, 4/2 equal to 2 edges. And we have the remainder of the surface. If we delete gamma, the given gamma is just a cell, because this whole surface is a cell, and it remains there. We don't identify anything here. The surface exactly embeds in the graph, in the surface T2. So we can decompose T2 using these edges and the interior surface, right? Surface means really two-dimensional cell. 2D. Okay. So basically, this is like open disk T2. That's good. Okay, so let's see what happens in this case. So in this case, if you do these gluings, you do get a sphere. But now the graph becomes a graph with 3 vertices and 2 edges. 2 edges, of course. So we get 3 vertices. 4/2 equal to 2 edges. And 1 face. It's called face. The next possible gluing is these two, okay? And these two, we just get, again, a sphere. And then we've got similar situation. So exactly like this. Get 3 vertices, 2 edges, and 1 face. Okay. So now we want to relate these two things, the calculation we did over there and the calculation we are doing over here together. We want to relate them. So how we are going to relate them? That's let's see immediately what's going on here. So we want to see that actually trace of, yeah. Okay, maybe before doing that, okay, let me not go into that. Let me just talking about, so in general, yeah, this is better to start. In general, consider a 2M gun. So for example, for M equal to 3, we just get a six-gon, and we have many pairings, right? So how many edge pairings? Well, we know how many pairings. I mean, in first lecture in Gaussian integrals, we saw how many pairings a set of 2m elements has. It's 2m minus 1 double factorial, right? So this has 2m minus 1 double factorials. In this case, we have so m is 3 in this case. Okay, so m is 3, we get 5 double factorial. And if you compute 5 double factorial, 5 times 3 times 1, which is 15, right? So 15 pairings of this six-gon. Six-gon. Okay. So when we do these pairings and we glue along each pairing, we get a surface, closed surface, right? So here the surface. This surface is going to be always oriented and without boundary. Oriented without boundary. Right? So, I mean, for example, in this case, you can start with this. Okay. Try to imagine when you glue this, what kind of surface you get. It's not very pleasant activity to do that. I can tell you. And so in this case, for example, what we get is not clear. And in general, what happens? So you get the topology of the resulting surface. We need a little bit of topology. We need a bit of, so we need to discuss the idea of Euler characteristic.
Professor,
Yes,
I've got a question.
yes.
It seems like you're not considering identifying the edges like when the orientations are opposite, like to get a Klein bottle or a projective plane.
Yeah.
So is the convention that basically you're identifying them according to these dotted lines that you're drawing to
Exactly.
avoid twisting them?
Exactly.
Okay.
Exactly. Yeah. We do get only oriented surfaces, so certainly no Klein bottles or projective plane. Those will be important when you consider real symmetric ensembles. So real symmetric matrices, when you consider, those will come up. In the complex case, life is much easier. So we only get these oriented closed surfaces.
Okay.
And going into real symmetric matrices is more complicated, and even some results are not. I mean, these results are known, but some results are still not known in that case, or very difficult to get. So, yeah, that's a good question. Oh, I have several questions in the chat, or maybe comments. Wow. Isn't a square a closed manifold with corners? Yes, we are, but we are looking only at these things topologically, so it doesn't matter for us. Yeah. Yeah, I mean, we are not looking at these surfaces as anything beyond topological manifolds. So, yeah. Okay, good. So I can now go back to this. Okay, so now, so what is Euler characteristic? Okay, so I want to be a bit more general than just for surfaces. So it's good to have this general thing. So let X be a topological space. Then you can try to define its Euler characteristic, phi of X, by the following. This is a standard definition by the following alternating sum. The sum, I say 0 to infinity minus 1 to the I dimensional, say, over R, hi of X and R. So this is the alternating sums of dimensions of, for example, cohomology groups of this space. I mean, obviously, for this to make sense, we must have hi xr equal to 0 for I large enough, and each of them should be finite dimensional. So these are the two necessary conditions. The dimension of hi xr is less than infinity for all I. And these two conditions are assumed in this definition. Then we get an integer called Euler characteristic. Is a topological invariant of the space. So being topological invariant means that this can be computed in many ways, right? So now if X happens to have a simplicial decomposition, if X has a simplicial decomposition. So its cohomology can be obtained from a finite dimensional complex, C0, C1, C2, say CK, and then 0. So there is this differential delta. Now, these CIs is a vector space that's generated by I-dimensional cells. It's a vector space having I-dimensional cells. I'll give a quick example very soon. I-dimensional cells. And your space is k-dimensional, so there's no need to include k plus 1 dimensional cells, but that's enough. Okay. Then we know that the cohomology of this guy actually is isomorphic to cohomology of this complex. Is hi of C, this complex I call it C, which is kernel of delta divided by image of delta. Now, but the good thing about this approach is that you can immediately prove Euler's theorem in this case, in this general case. Euler has a nice theorem, which was proved in the middle of 18th century, but then it was generalized by Poincaré. So then we have Euler's formula. In this case, it just becomes a piece of linear algebra, namely sum minus 1 to the I, dimension of Ci, where I is equal to sum minus 1 to the I, dimension of Hi C. So this is, again, like I had a result mentioned for graphs. I said that it follows from rank plus nullity theorem. This also follows from rank plus nullity theorem. Okay, so this is pure linear algebra. Linear algebra, rank plus nullity. I mean, you have to be a little careful, but that's not difficult. Rank plus. I mean, okay, so this is. So the good thing about it is that now we can compute Euler characteristic without computing cohomology directly from number of chains. So a corollary is the actual original Euler's formula. Again, for surfaces. Is that actually, if you have a surface like this, so imagine this is equal to x. If you have a triangulation with v vertices, or the number of vertices, e number of edges, and f equal to number of faces. So imagine you decompose this by, you triangulate it by these triangles, or it doesn't matter with what, it just so on. If you do such a decomposition, then you know that the Euler characteristic of x is equal to the famous Euler formula, number of vertices minus edges plus number of faces. This is what Euler proved for genus 0 surfaces in 18th century. He didn't talk about what genus for these things. He was not known. He used a different language, but that's. But we know that this guy is equal to the Euler characteristic of x. Actually, it's equal to 2 minus 2g. This calculation of Euler characteristic is a famous one, and this g is the number of holes, which is genus now. So let me here. So this is a theorem that I won't prove is something standard in topology of surfaces. Theorem that actually I just say for any oriented surface with genus G and P boundary, or any orientable, I would say, surface with genus G. And B boundary. Boundaries. So we are talking about something like this. So here is G is equal to 2 and B is equal to 3. The Euler characteristic. So it's a formula that generalizes this formula, and I need that formula later on, but so I just write it's 2 minus 2G minus B. It's 2 minus 2G minus B. It's a general formula that's in algebraic topology immediately improve. So first graduate course or undergraduate improve these things.
Are the boundary components always circles?
Yes, the boundaries are one-dimensional closed manifold, so topologically, again, they are going to be circles here. Yeah. Okay, now one thing to take away is to realize if B is equal to 0, it means no boundary. The maximum value of Euler characteristic is 2. That's for a sphere. So it's good to have this sort of picture in mind. So here is G. So G, if G is 2, you've got a sphere. And if G is 0 is the next one. So this is you've got a sphere. So let me write this. G equal to 2, we have got sphere.
Is that
G, huh?
sorry, G equals to scale?
Oh, no, Euler characteristic. Yeah, very good. Yeah, thanks. Yeah, Euler characteristic equal to 2, we have a sphere. Euler characteristic equal to 0, we have a torus. Then Euler characteristic is negative. I mean, so the majority of Euler characteristics are negative. So then chi equal to -2. So this has a surface. So let me write here. Then, as Shivik said, this is G equal to 0. This is G equal to 1. Here is G equal to 2. And so on. So, I mean, these first two cases are mildly interesting, especially the middle one, the torus, elliptic curves, and these things. But the most interesting things are here in genus bigger than or equal to 2. So there are infinite number of them, and they form, eventually they're going to play a big role in hyperbolic geometry. So they are the hyperbolic surfaces. They play a big role in the story at one point in random matrix theory. Okay. So have this in mind always, that there is this relation between genus, Euler characteristic, maximum value of Euler characteristic, minimum value of genus. So they go in the opposite directions. Okay. Now, we need something which is a bit more general than this, which is, so let me give a definition first. That's the definition of one-phase map. So a one-phase map is a graph gamma, which is actually drawn on a surface. on a surface. As always, orientable without boundary. Such that the complement of this graph on the surface such that S minus gamma is a two-cell. By two-cell, I mean this is homomorphic to the open two-disk. S minus gamma open two-disk. Okay, we saw some examples of this already by gluing surfaces. And in general, in general, by gluing a 2M gun, say here 6 gun, for example, 2M gun, along some pairings, we obtain a one-phase map. One-phase map. And this one-phase map is basically completely determined except for this number of vertices with V vertices, which it depends on what we want. I mean, it depends on how we glue. So it depends on gluing. So this depends on gluing. E equal to M edges. That's independent of gluing because we have got, after all, we're identifying 2 by 2 these edges. So we have 2M edges originally, and we identify them 2 by 2, so we're going to get M edges. This one. And F equal to 1 face. So the only thing that's in this one-phase map that's not determined and depends on the gluing is the number of vertices. It's always the number of vertices in this case. Okay. So then we need a relation between Euler characteristic of the surface and this one-phase map. And that's why we need a bit more general version of this Euler theorem for one-phase maps, which I write it here. And then you see. So Euler theorem for one-phase maps. So the Euler characteristic of the surface that you obtain, which is 2 minus 2g, is actually equal to V minus E plus F is equal to V minus M plus 1. Now, So it's a bit hard to accept this as Euler's theorem at first. I tell you what's happening. This is not quite a triangulation, you see. So let's look at the example. There is a problem here that we have to discuss a little bit. It's not a problem, but there's a subtlety. So imagine when we triangulated, when we glued the opposite, no, not the opposite, the non-crossing things, we got this, right? This was our gamma. So we have got V equal to 3 here. Number of edges is 2. Number of faces is equal to 1. And of course, the Euler characteristic is equal to 3 minus 2. Number of vertices is, yeah, that's fine. We get 2. So this predicts to be a sphere.
Plus one.
Should be. So we get 2, right? And it should be 2. It should be 2 because Euler characteristic of the sphere is 2. However, it's hard to accept this at first. It's hard to accept this as a special case of Euler's theorem because this is not a triangulation. That's the subtlety I want to mention. It's really like degenerate triangulation. So there's a problem we have to address. But the way out is to actually cut the surface along this line a little bit, add an extra edge here, and you add an extra edge here. Then you get 2 more cells here. And now you can apply Euler's theorem to this sort of triangulation. And you see that this quantity does not change by adding this. So in general, it is possible to give a proof using this technique, but I won't write the proof, but it's a good exercise to do. Okay. So here is warning is that. So star is not immediate. It's not exactly Euler's formula, but it follows from that. But can be derived from Euler's formula. Okay. So that's where we are now. Okay. Now, we're going to now identify some gluings as special for what we want to do. These are non-crossing gluings.
Oh, just one question. I think with the 2M gone for the
Yes.
Riemann surface of genus G, say it usually has to be a 4G gon, like the octagon for the Riemann surface of genus 2, but the hexagon it gives a pinched torus, or it has
Yeah, you're thinking in terms of pairs of paths and the Riemann surface structure actually. But here we are thinking of them topologically only. So I don't need to get 4M gons.
true. So it's just an isolated kind of
It's really
it can be
a
smoothed out.
topological surface.
True.
So that's why it's called topological expansion or eventually or genus expansion. The Riemann surface structure, yeah. So if you want to decompose it in terms of pairs of paths or in hyperbolic geometry, yeah, you need to start with 4m gone. You're absolutely right. Yeah.
Okay.
Excellent. Yeah, very good. Very good. It was a good comment. Thank you. Yep. All right, now, so let's see, let's discuss a little bit non-crossing pairings. So again, so in the hexagon, so some pairings are like this. So this is non-crossing. But then some pairings, they can be crossing over each other. Like this one, it goes over this and this. So these two cross each other. So these are crossing pairings. Right? Okay, so now what we need to identify is that what is the importance of non-crossing pairings? So the importance of non-crossing pairings is that when you glue, that's exactly the case where you get a sphere. So there's this lemma, a gluing of 2m gon gives a sphere. It's also called, we just say is planar. This is standard physics terminology because physicists think of a sphere as punctured sphere and then it's planar. That's physics jargon is like that. It's called planar. And the lemma says that a gluing of a 2m gon gives a sphere is planar if and only if it is non-crossing. Okay. And I can add if and only if the graph gamma that you obtain in the one-phase map, the graph gamma is a tree. It's a tree, like the cases that we had here. So this is not accidental. In general, we get this. So, of course, the total number of pairings is 2m minus 1 double factorial. This is what we saw for pairings always. Is equal to 2m minus 1 double factorial. And then there is a certain subset of pairings which gives us non-crossing. Let Cm equal to number of non-crossing pairings of a 1. So what we need to do immediately is to identify these numbers Cm numerically. So we'll prove that very soon, actually, that Cm. Our immediate goal is to show that Cm is equal to the nth Catalan number, famous Catalan number. Which is equal to 1 over m plus 1 to m choose n. Right? So I'll just go for 5 more minutes and then I'll stop. If that's okay. Is that okay? So how we can prove such a thing? I mean, the idea of proof. So this is one definition of Catalan number I gave you. Catalan number is the number of non-crossing pairings of 2m dots on the plane or 2m line. So there's a famous thing. I think people have counted this in Richard Stanley's book on combinatorics. There's an exercise, he gave 140 different definitions of Catalan numbers. So Catalan numbers is one of the most important sequences in mathematics. It's amazing. It appears in many, many places, especially in quantum field theory, in combinatorics, in many, many places. It's just an incredible thing. Yeah. So, okay. I think actually, because if I want to start that, then I have so this proof of this. I mean, this is not difficult actually. I leave it to you guys as an exercise. I may come back to that later, but my immediate goal next lecture will be to prove this, to find by writing the recurrence relation, and that recurrence relation is very, very important. Because actually, that's a special case, very trivial case of Schwinger-Dyson equations in QFT. It's a prototype of those equations. And then we will relate polygon gluings to tracial moments of GUE matrices. And we use that then to prove Wigner's semicircle law is the next immediate goal. This is the eigenvalue distribution of these things, and we'll go. Are there any questions in the audience? Let me just see. Oh, there are a lot of comments or questions. Oh yeah, so this is yeah. As I said, I mean. Yeah, but you're thinking smoothly. Just think about it completely topologically. These are topological surfaces, yeah. Okay, very good. Thank you very much. So I just say goodbye to the Zoom audience if there are no questions. Bye-bye now.